Okay, so good morning, everyone. First of all, thank you for taking a few moments and filling out the survey. I very much appreciate your feedback. If you're still working on one, that's fine. Just bring it down at some point before you leave today. But I'll look these over the weekend and see what you have to say. So thank you very much for doing that. Second thing, remember that we have our quiz on the data security unit on Monday at the end of class. The homework assignment for the new organ donation unit that we started last time will be posted, I'm hoping later today. It may not be till tomorrow. And then I'll announce the due date and the quiz time at that time. It depends sort of how far we get today. So we'll see how that goes. Does anybody have any other questions before we jump in today? Okay, so I guess for one other announcement, remember the term paper first draft is going to be due in just under 2 weeks now. So it'll be due a week from Monday, which is, I believe, the 30th of October. I will be posting on Blackboard the submission portal over the weekend. I'm going to say this now, and I will say this a lot more strongly on Monday. The peer review system on Blackboard is extremely rigid. Okay, so I'm going to set this up, and I'll show it to you on Monday, and we'll discuss it. But just bear in mind, I have very, 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 very extremely limited options to fix any issues. So like some of you know that if you upload the wrong file on the homework or you want to change something, I can make a resubmission. I can't do that on the term paper, at least not for the first draft. This peer review system is extremely rigid. So there's going to be a couple things in that we'll discuss on Monday, but just be warned, that's coming. And all that. Does anybody have, I guess, again, any questions before we jump in? Okay, so if not, then last time, remember, we had sort of jumped gears a little bit. We finished our digital devices big unit, talking about storage and transmission and security and all that. And we spent most of the last lecture talking about organ donation. And so we saw, sort of what's the history of this and when did organs first start getting donated? What types of organs can be donated. And in particular, we started turning our attention to a specific type of organ donation. And which organ was that? Kidneys. Well, why were we so interested? What's so different about kidneys that they're going to warrant our special attention? Right. So basically, most people have 2 kidneys. You usually only need 1 to live. And so looking at kidney donation, we can start to consider the idea of live donor kidney transplants, where we don't need a cadaver to get it. Like normally if we want a heart transplant, you're not getting the heart from a living person. Okay? It's someone who was recently deceased for whatever reason. And so the idea now is, now that we have this living donor, we can start to try to match people up. So again, the idea is maybe I need a kidney. Okay? Both of mine are failing, and I need a kidney to live. Well, I can bring my brother, my sister, my friend, whoever with me, to say, well, they're willing to donate me a kidney. And what happens? If I come with that friend or that relative and they're willing to donate, what's the hospital going to do? Well, sure, they're going to check both of us out, look at blood types, or immune system responses, and try to determine, are we a match? Would my body accept my friend or relative's kidney? And if it does, if I would accept the kidney, what are they going to do? They're going to put us both in different operating rooms, and we're going to have a surgery, and I'm going to have a new kidney in a few days or a week later. Is that always the case, though? If you come in and bring that friend or relative, are you guaranteed that they're going to be a match? Not even close. And so what can we start to do then? And this is sort of where we left off last time. We can start to try to catalog all sorts of different pairs of people. So I'm one person and I bring my friend. Well, you need a kidney and you've got your friend or relative. But none of us, you're not a match for your friend or relative. I'm not a match for my friend or relative. But maybe I match your friend and you match my friend. And if we were to somehow work together, can we improve the standard of living and the number of lives saved by doing a little bit of creative matchmaking? Sure. Okay, so one of the issues that we ran into, just very, very briefly, was this idea, is that necessarily legal, what we just talked about? Well, actually, the answer is yes, but why is it legal? Because we passed an act of Congress explicitly making it legal. The issue is it's technically quid pro quo. Okay? Because we're saying, well, my friend will donate me a kidney, or donate you a kidney, but only if your friend donates me a kidney. You know, that whole, you do something for me, I'll do something for you, textbook quid pro quo. But we said in this case, that's fine. Yes, it's quid pro quo, it's not illegal. Okay? And so we can start going through these examples and start building up to see what happens. Okay, so we started with an early example. We've discussed this one where you bring your friend or brother and there's a match. And so where we left off last time, we've already sort of recapped example 2, and we ended with this example 3 where now all of a sudden we're no longer sort of textually describing what's going on, because now we've got 4 different pairs. There's 4 donors and there's 4 acceptors, and none of them independently match. So we can notice here that like on pair 1, the acceptor needs or has O-type blood. The donor has A-type blood. Okay, so is that necessarily going to work out okay? Can that donor necessarily give to that acceptor? No. Just as a note, for the purposes of the examples we will work in class, we're going to assume blood matches have to be an exact match, or blood types have to be an exact match. We could certainly relax that. You'll probably have a homework question relating something about that. But for the examples we're going to work, blood types must match exactly. Okay? So are any of these pairs able to independently do a transplant under those assumptions? Nope. So now the question then, looking at this table, we've got these 4 donor-acceptor pairs. How many of the people that need kidneys, how many of the acceptors can actually receive them based on the information we have provided here? Anybody look at this since lecture ended on Monday? Can anybody get a kidney? Okay, so I see you're saying sort of all of them can. So maybe if pair 1 donated to pair 3, okay, well that would work, right? And then pair 3 could donate to pair 2, who could donate to pair 4, who could donate back to pair 1. In this case, everybody, as it turns out, can get a kidney. Hey, that's pretty cool. Okay, so all we need to do is do a little bit of analysis here and see that, well, everything sort of worked out, and there were the 4 people, and 4 people can get kidneys, and great. And so the idea now is, how do we start to scale this up? So we did sort of the one example where there was 1 donor pair. And it's pretty easy to see either, yes, that surgery is going to work, or no, that surgery isn't. When we had sort of the 2 pairs, again, it was easy to see. And maybe with 4, it wasn't even that bad. But the idea is, you know, in the real world, are these registries going to have, you know, 4 or 5 or maybe 10 pairs of donors and acceptors? No, in the real world, it might have more than 10,000. Meaning there's more than 10,000 people needing kidneys and more than 10,000 people matched with them willing to donate, but not actually matched in the sense that they can exactly give to the person they're paired with. And so the big question that we're trying to get at here is, how do we actually then go about finding matches? If I were to give you a table of 10,000 pairs and blood types, how many of you think that'd be a great homework question? Okay, you're all glazing over more than usual. So I agree, that would be awful. I think that sounds really tedious and just really, really obnoxious. But yet, is that an important problem that we want to solve? Yeah, because we want to save these lives. We want to help as many people as we can. And so what we're going to start to work on in this unit are sort of these 2 questions here. Can we somehow visualize the donors and acceptors? Okay, so what's a way that we can try to do this? Again, the human visual cortex is an extremely powerful machine. If we just look at a table, is it maybe all that obvious what's going on, versus if we have a better way to visualize it, might it be clear what we need to do? Okay, so we can work on that. And then we can sort of, once we have this idea of what does this registry look like, what are all of the people available for doing the kidney transplants, how can we use some mathematics to help us solve the problem and save the most number of lives possible? So that's where we're going to head as we work through this unit. Any questions on that? Okay. So then basically the key mathematical tool we're going to need as we move through this unit is something called a graph. Who wants to take a guess, or who knows what a graph is? Something that shows data. Something that shows data. So you're thinking something like that? So there's like y is a function of x, or we can make our plot. Yes. Okay, so something like this. Is this a graph? Yep. This is not the type of graph we're talking about. Okay? We're not going to need to do a whole lot of plotting for this. Instead, what we're going to look at is this type of graph that we've got here pictured on the right. And we'll talk about what this is more in a moment. But basically, you've got a graph where there's all these different things that are sort of connected together. And if that sounds abstract, again, we'll get there in a moment. Just as sort of the note, as we're moving on here, Wikipedia has some nice information. Khan Academy has some great links. If you're looking for more information on graphs, you can find some there. Certainly, if you're really interested and want to see more, a discrete mathematics course, something like AMS 301 will tell you more than you ever wanted to know about graphs. Okay? So basically, this type of graph, what it is it's made of vertices and edges, and the edges in particular connect vertices. Okay, again, that sounds really abstract. So typically, and this is going to depend on your application, we'll go through some different examples here. A vertex is just an object. Okay, so it can be whatever object we have. Maybe, pick a noun. It's a person, place, thing, something like that. And then abstractly, these edges are going to be relationships between the two objects. Are object 1 and object 2 related in some way? Okay? And so what this graph here is plotting is, so we would say this circle here with 1 in it, that's a vertex. And we've labeled it vertex 1. We don't necessarily have to put the labels if we don't want to, but in a lot of cases it helps. Okay? And so then what we can do is we've got vertex 1, there's vertex 2 down here, 3, 4, 5, 6, etc. And what the lines are showing that are connecting these vertices are the edges. And so what this schematic is depicting is to say, well, we've got 6 different vertices, nominally 6 objects. I haven't given a context as to what they actually are in this case. But then we know from the drawing that vertices 1 and 6 are related, whatever our relationship may be. Vertices 6 and 5 are related. Are vertices 2 and 6 related? No, because we didn't draw the line between them. Okay? So we can start to develop quite a bit about the relationship between these different objects by looking at it in this visual schematic. Okay? So I think some examples are in order. So can you think of examples of graphs where we might have, what are vertices and edges? What's the graph? What are the objects? What's the relationship between objects? Have you seen, whether you've thought about it in this way or not, have you seen graphs in your day-to-day life? Or seen applications for them? What might be some applications? Yeah. Yeah, these types of graphs where we've got the vertices and the edges. Food chains. Okay, so yes, that's a great answer. I've got a picture for that that's like 3 slides down, so we'll come back to that point. But absolutely, food chains and food webs. Maybe we'll ask the question now. What's the vertex? What's a vertex in a food chain? Well, some organism. And what are the vertices? Or sorry, what are the edges? Right, so one eats the other one. And so we know that we can start to have all of different objects and they're related in some way, and we can connect them like that. But yeah, absolutely, a food web or a food chain is a fantastic example. Can you think of other examples? Yep. Okay, so that's the first one we've got here. Maps. We can think of maps as a graph. What might the vertices be in a map? Different locations. So maybe they're landmarks, maybe they're buildings, maybe they're intersections of roads. I don't know. Maybe it's some small lake or pond or river or dock or whatever the case may be. What are edges necessarily going to be between those vertices? What's the relationship between them? Okay, is there a road or is there a path between them? Okay, can we get directly from one vertex to another, from one place to another along that? Okay, so absolutely, maps are a particular one. Maybe also if you don't want to do roads so much, you could think about train stops or airports as maps. So here's all the airports and they're connected, saying, does a train run directly between them or does an airplane fly directly between them? You could make a graph out of that as well. Another example, social networks. Dare I ask, how many of you use Facebook? Okay, the rest of you aren't listening. I get it. What might a vertex be in Facebook? What's the object? You. You are the object. And what might the edge be that relates different objects? Being friends. Okay, so we can draw a whole big map like this and say, well, you're friends with this other person who's friends with this other person. who's friends with this other person, and start to make this whole big map to see who's friends with whom. Has anybody ever used, there's the friend finder on Facebook or the friend suggestion thing? How do you think that works?
If you're connected with one person, so if you're connected by Edge,
well, so the idea is you're going to have friends and you're going to connect, and what the algorithm is going to do is look at your friends and say, well, who are they connected with? And it's going to try to look over all of your friends and see how many of your friends match another person. And if there's another person on Facebook that you're not friends with, but you have 180 mutual friends, is that someone you might know? Yeah. If, on the other hand, there's a friend of a friend and you only have one mutual friend, which is to say the one friend that's a friend of a friend, is it likely that you know that person? I mean, you might not. But as the number of sort of mutual friends increases, the likelihood that Facebook says is going to go up. And it can try to draw a graph like this and traverse that to make recommendations for you. Is this someone you know? What might be another instance of a graph in a different social networking tool? Anybody use Twitter? Okay. What might a vertex be in Twitter if we wanted to make a graph representing the Twitter sphere?
You'd have the original tweet and then like the retweets.
Right, so you could have, yes, you could have original tweet and followed by retweets and sort of span how this all goes. You could also say, here's a different user and who follows that user. Okay, we'll come back to that point in a little bit because we can distinguish when we get a little bit later on Facebook from Twitter in this regard. Okay, as we've already mentioned, we could have food webs where we've got different organisms eating other organisms and looking at who eats what. Okay, what about the internet? Could we think of the internet as a graph? Yeah, so what are the vertices going to be, again? What was that? It might be a website. There's probably a slightly better one. We could do it that way, but when it comes certainly to when we get to the internet in a couple of weeks, we're going to make a different choice. Could be an IP address, or more specifically, some device. So some computer, some router, some server, some device that's hooked up to the internet. And what are the different edges going to be in that graph? All of the actual connections. What other devices is that device connected to? So I notice a bunch of you have your computers out right now, which is good because we're going to get to that example here in a few minutes today. What device on the internet is your computer connected to right now? Well, if you look up, there's probably some router stuck up on the ceiling, some wireless router, and you're connected to that right now through WolfieNet Secure. But that's the device you're connected to. And then that router is connected to something else, which is connected to something else, which connects to Amazon. I don't know, whatever website you're on right now. I'll assume you're buying me a present on Amazon. Okay. Getting maybe a little bit more serious, certainly like in chemistry or other areas of science, we can see graphs. So maybe looking at a molecular structure, what are the different atoms and how are they connected to each other? Are there bonds between them? Could we make a graph to represent molecules? Sure. So the idea here is there's lots and lots and lots of different applications for a graph. Coming back down to that key concept, we're going to have vertices and edges. A vertex is just an object, and an edge is just a relationship between them. Of course, what the vertices actually represent, what are those objects? That depends on your application. What's the relationship between them? Again, depends on your application and what you're trying to do. But this turns out to be an incredibly powerful tool for visualizing relationships between objects. So maybe we can get sort of into a more pop culture example of graphs. And I know this is a little bit dated. Has anybody heard of or played the game 6 Degrees of Kevin Bacon? Okay, so there's a couple hands. How does it work?
Oh, is that you start off with like either yourself or some other person, and your goal is you have to try and connect through relationships like that person to Kevin Bacon.
Okay, so the idea is, I'm gonna paraphrase a little bit and add a little bit more detail in. So the idea is you're going to start with some actor or actress. Okay? And what you're going to try to do is to say within 6 steps or within 6 relationships, link that actor or actress to Kevin Bacon, where the relationships we're going to use are they starred in a movie together. And the idea behind this game was back in the 1990s, Kevin Bacon was in like every movie that was ever made, at least in some 10-second bit part. And so this was a really annoying game that my friend loved in middle school. And so the issue is, I mean, this game has somewhat become a bit of an anachronism because of this tool that now exists called IMDb, the Internet Movie Database. Okay, but before that, this was actually somewhat of a challenging game. And so for an example, we might say, well, we have an actress. Her name is Robin Wright. Can we get to Kevin Bacon in less than 6 steps using movies that both of them have starred in and intervening actors or actresses? Can we take a guess without looking up on Wikipedia how we might get from Robin Wright to Kevin Bacon? Okay. Certainly, is there a unique answer to this question? Nope. One way that came to me, again, being a 90s person, well, Robin Wright starred in Forrest Gump with Tom Hanks. Everyone's seen Forrest Gump? Okay, fun movie if you haven't seen it. Tom Hanks starred in Apollo 13 with Kevin Bacon. Okay, so we can see that Robin Wright is 2 degrees away from Kevin Bacon because we had these 2 jumps to get from her to Kevin Bacon using those relationships of did they star in a movie together. Sort of the more 21st century example of this 6 degrees game is what's maybe called 6 degrees of Wikipedia. Has anybody heard of this? Okay, more hands go up. Good. So the idea is, Wikipedia has a lot of stuff on it. And the pages are all very interrelated. If you go to any one arbitrary Wikipedia page, there's going to be a whole bunch of links to other things, whether to dates, whether to places, whether to other concepts or other terms, lots of links. And so the idea here is because Wikipedia is so well connected that you can probably get from any one Wikipedia page to any other Wikipedia page in 6 links, which means that you can click 6 hyperlinks. Okay? So what we're going to do is play a little bit of a game here where I've got a couple starting and finishing prompts. So what I'd like you to do, we're going to hand back the quiz from last week while you do this as well. But there's a couple different prompts here. So maybe start at XKCD, the webcomic that we keep seeing pictures from, and see if by only clicking on links in Wikipedia, so start on the XKCD Wikipedia page, by only clicking on links, can you get to Jurassic Park? Okay? And count, what's the path that you took to get there? What are the links you clicked on, and how many links did you have to click? If you finish that one, maybe try 6 and get degrees. And if you're feeling really ambitious, you can try Journey to the Center of the Earth. That one's a little bit weird, I'll warn you. But anyway, so go ahead and take some time. We'll hand back the quizzes here while you work on that. And then once everyone's got their quiz back, we've taken a few minutes, then we'll come back together and sort of see how does this actually work. Okay? Okay, so has anybody found a path from XKCD to Jurassic Park? Okay, we've got a couple.
So there's on the XKCD page, it talks about an early session with Velociraptors. If you click on Velociraptors, you go down to popular culture on Wikipedia and get Jurassic Park.
Yep, I think that's the one I found. So we can start with XKCD. And scrolling down, because he loves to do dinosaur things, there's somewhere here where it talks about velociraptors, like right there, so we can click on Velociraptor. And sure enough, these were featured in Jurassic Park. And there we go. So we had 2 links. If we wanted to think about this as a graph, what we might have done is start. So we have our web page, and is that going to be a vertex or an edge? It's going to be a vertex, right? So we can sort of draw the little circle around it, again, and use XKCD as a label, okay? What was the next page that we found? We had Velociraptor. We have another vertex. And was there an edge between them? Yeah, because what are we using as our edge? What's our relationship? There's a link. Okay, so we can draw that. And then our last page, we had Jurassic Park, and we could also draw the edge between those. So pretty simple graph. In this case, it wasn't that hard to get there. But maybe some of the other examples were a little bit more challenging. So did anybody see from 6 to degrees? Yep. How do you do it?
On page 6, it specifies a 6-sided polygon.
Okay. So let's come back over here. We can start on the Wikipedia page for 6. And so it was down here you saw there was polygon. A little further down. Oh. Yep. So we've got there. So we got 6-sided polygon. We can click that.
And then degrees is on that page.
Yeah, I imagine it is. So we can say degrees is on here somewhere. What was that? Yeah, I was going to say that's probably a good idea. So we can do Control F and just find. And sure enough, there's nope, that's not a link. So we can continue looking for the next one. There we are. That one's a link. And so we get from 6 to degrees through polygon. Okay? Also not too bad. For the weird one, did anybody get from Journey to the Center of the Earth? This one's insane.
There are a bunch of different links for Journey.
Yep.
Start with the band.
Okay, so one of the issues that you immediately came up with, if you type in Journey into Wikipedia, is that a unique identifier? No, it's not. Okay, so we can come in here, we can type in Journey, and just hit enter, and it immediately comes back to, well, I don't know what you actually mean. Do you refer to a road trip or travel or a day's journey? Maybe we're referring to William Journey, a Missouri senator from the 20th century. Maybe we're referring to films called Journey, literature, different albums, certainly the band, songs, video games. Okay, apparently there are other uses. Let's suppose now, so one of the issues that we have playing this game is where did we actually start? Did it specify any of these pages? Okay, so let's assume it was Journey the band. Okay, we're feeling rather retro this morning. Anybody have an idea what we can do to maybe get from Journey the band to Center of the Earth? I'll warn you, this one's crazy. At least the way that I found. Okay, so we can do it in 5 steps. And the way that I was able to do it, can scroll down here. So we start from Journey the band, and we can go to Billboard Hot 100. Okay, so from Billboard Hot 100, well, that's getting us sort of closer to the center of the Earth, right? Maybe. We can come down here and we'll find at some point where it's talking about the history that one particular artist's name is going to come up. And that artist is going to get us a little bit closer to the center of the Earth. Does anybody want to take a guess who this well-known artist is that was on the Billboard Top 100 for a long, long time? Elvis Presley. Okay, so this is sort of like getting closer to the center of the Earth again, right? Because Elvis was sort of near the mantle. I mean, maybe. Okay, so now that we're at Elvis Presley, where do we go? Okay, well, We're going to scroll down here a little bit. Okay, we don't care about maybe his early life. We're looking at when he starts becoming a star. And he did some appearances. Scanning for the link here. If I don't see it in a moment, we'll just Control F it. Okay, where is it? There we are. First national TV appearance. So he appeared on a network called CBS, which I'm looking for the link. I'm not seeing it. Okay. There it is. So down here, he appeared on CBS. Okay. How is this getting to the center of the earth? This is the beauty of this game. Until you get to the end, you have no idea you're headed in the right direction. That's sometimes the fun part. Okay, so CBS has had lots of different TV shows over the years. What are a couple that you can think of? Okay, NCIS. Sure, that's a popular one now. Others? No one watches CBS. Good to know. Okay, so one of the ones that was big, thinking on our 80s motif of starting from Journey back in the 1980s, the band, one of their big 1980s TV shows, not really that popular at the time, but it certainly gained a cult following afterwards. Several movie franchises that have been rebooted lately, was a cartoon show for children. Does anybody know what it was called? It is not Magic School Bus, but that's an interesting idea. Looking for the link in here. Okay, well, we're going to Control F it. Teenage Mutant Ninja Turtles, again, the 1987 version. Okay, so really, this is getting us closer to the center of the earth. Trust me, it is. And so if you scroll down in here, we're not going to search, I'm just going to Control F it in a moment. But there was one episode of the show where something was going on at the Earth's core. So we're going to keep searching here. And we can click on Earth's core, which takes us to, okay, structure of the Earth, center of the Earth, the core. Okay, so there's a little bit of give and take. But we could go Journey the Band, Billboard Hot 100, Elvis Presley, CBS, Teenage Mutant Ninja Turtles to get to the center of the Earth. And somehow that still sounds less complicated than any of the Rox movies. Because there was the journey to the... Okay. That was the revised one, yes. There's an even older one that actually wasn't that bad. The graphics were cheesy, even though they were awesome by like 1960 standards. Okay, yep, the book. Okay. All right. So anyway, you can have some fun and see that, again, graphs start to appear all over the place. And we saw them sort of in pop culture. There was Kevin Bacon. You can do the 6 degrees of Wikipedia. And we could, again, draw that as a graph by taking each of those web pages we clicked on, making them a vertex, and drawing the edges between them to show that we were able to click to get from one to the other. So for another example, there was this warm-up puzzle back at the beginning of the day where here's the picture of the 50 United States. And we could ask, how many colors do we need to color the map such that no two adjacent regions or no two adjacent states get the same color? Does anybody know the answer to this question? What's the minimum?
4.
It's 4. Okay, well, we know it's at most 5. Actually, is there 5 or 6 on that? There's 6. So there's 6 colors on the map here. So we know the number's at most 6, because clearly we can do it. You can look at the map that's on the screen, and no two adjacent states have the same color. Okay, so how might we consider this problem?
Is this related to the Carlsberg Bridge problem at all?
Is this related to the Carlsberg Bridge problem? A little bit. We'll actually come back and we'll see that in a few weeks. Okay? So the idea is we could make a graph out of this map. And what might each vertex be? A state. And the edges, the relationship is they're adjacent to each other. And so what we can do is a slightly different problem that we can look at with graph theory and using these graphs is to say now color each vertex and just make sure no two adjacent vertices, no two that are directly connected, have the same color. And it turns out, so people figured out a long time ago that you could do it in 6 colors. Back in the 19th century, it was established and proven you can do it with 5 colors. It was then quite a hot topic for about 100 years. I know this is sort of esoteric math history, but it's kind of a fun story. Every map that anyone had designed, basically from about the mid-19th century up until about 40 to 50 years ago, could be colored with 4 colors. You could pick, if you had red, yellow, green, and blue, and you had your map, you could color it, and you could have all of the states or regions or whatever colored such that no two adjacent regions have the same color. But it hadn't been proven that you could do it in 4. In the 1960s and 1970s, the first proof finally became available that you could do it with 4 colors, but it was extremely contentious to the point that the math community did not actually fully believe it for about 20 years. You may want to take a guess why that might be. And this is sort of a fun story. So around the 1960s and 1970s, we saw the emergence of what sorts of digital things came available in the 60s and 70s? Oh, computers. Okay, so it turned out this proof was incredibly complicated and had about 190 different cases that had to be considered. And so you could think about some poor math grad student sitting at some desk having to sit there and go through all 190 of those cases independently to make sure that they all work out. Okay, that could happen. The easier thing is they said, well, let's take all of those cases, let's put them on a computer, and have the computer try to reason, does this work or doesn't it? And it took, I think, about a year's worth of computer time at that point in history, which means to say it would run in a few seconds on your phone. Probably less than a second on your phone, quite frankly. But it ended up going through all 190 of those cases and found that, in fact, they all worked. And the computer then spit out a proof saying, here's case 1, it's good. Here's case 2, it's good. It amounted to, I think, over 300 pages of documents that was basically written in computer gobbledygook. And so this was the proof. And so the math community then said, well, number 1, is this proof even right? Because a person didn't do it, a computer did it. Okay, so, and how long is it going to take us to go through and sort of check all of this that it actually is going to work out? And, okay, well, that's sort of tedious. Then there was the bigger question. We were talking about legal issues last time with organ donation. Maybe a different legal issue in this case. Who actually gets credit for the proof? After all, the two guys that wrote the computer program didn't actually do the proof. The computer did the proof. So does the computer get credit for solving the problem? Or do the 2 guys who wrote the program that told the computer how to solve the problem get credit for solving the problem? Okay, we've now sort of established that the latter is what happens. The computer doesn't get credit. Okay, but these are some contentious issues that took about 20 to 25 years to work out. And it is now, people have gone through, they've checked that proof, it works. You can take any map like this, and with 4 colors, you can do it. But that was sort of a really neat advance in graph theory and being able to use these graphs to solve sort of long-standing problems. Just if you're curious for fun stories. Okay? And again, if you want more information, there's a Wikipedia link there on the proof and how that process worked. So now that we have this idea of graphs, we've seen edges, we've seen vertices, we've seen several different applications for what graphs can do. What we now need to do, sort of starting to head back towards our organ donation and our kidney transplant examples, is need to introduce some adjectives to help us describe graphs. Okay? Because that's going to help us solve different problems. And so one of the distinctions or the characterizations that we're going to make for a graph is asking, is it directed or undirected? And what this is asking basically is that relationship, so however we're forming the edges, we say vertex 1 and vertex 2 are related. Is that relationship symmetric? That is to say, if A is related to B, vertex A is related to vertex B, is vertex B related to vertex A? Do we necessarily think that that's going to be true all the time? Not necessarily. Well, let's consider our social networking example. So in Facebook, we said we could have a vertex is each person or each user, and the relationship is they are friends with each other. So if I am friends with you on Facebook, so that's saying I am vertex A, you're vertex B, and that's a relationship. Are you friends with me? Yeah. That's the nature of friendship on Facebook. So is that a symmetric or a non-symmetric or asymmetric relationship? It would be symmetric, because if I'm friends with you, you're friends with me. And we would call that graph undirected. Okay? Because there's that relationship where we know if A relates to B, B has to relate to A. Think about it now on the Twitter side, where we had each vertex was some user, and the relationship was some other user is following that user. Is that a symmetric relationship? If I'm following you, does that necessarily mean you're following me? No. So we can start to see that there are these things, there can be symmetric relationships, there can also be non-symmetric relationships, or asymmetric relationships. Again, depending on what is the nature of that relationship. So if we take a moment and sort of think about another example, let's come back to our 6 degrees of Wikipedia here. We could draw this graph going from XKCD to Velociraptor to Jurassic Park. Do you think, when we're doing the 6 degrees of Wikipedia, is this a symmetric relationship for this graph, or is it an asymmetric relationship? So the relationship that we saw was we could look at the XKCD page, and we found that there was a link for Velociraptor. Does that necessarily mean the Velociraptor page is going to have a link back to XKCD? No, it doesn't. So is this graph going to be directed or undirected? It's directed. And the way that we would normally denote that is, for a directed graph, we're going to put arrows on our edges, indicating the direction that we have to go. Okay? So now, looking at this graph, we can say, well, we started at XKCD. XKCD, we know, goes to Velociraptor. Does Velociraptor go back to XKCD? Based on what we have drawn on the graph, no, it doesn't. Okay, now in reality, we could go look at the Wikipedia page for Velociraptor, and I'd probably say it's 50-50 odds that there is a link back to XKCD. I don't know, we could go look. So it's possible that link exists, but based on what we have drawn on the graph, we don't know. Okay? And likewise, does Jurassic Park link back to Velociraptor? It probably does, but in this particular graph that we've drawn, no, it doesn't. So if we were on Velociraptor and wanting to play our game using just this graph, the only place we can go is Jurassic Park. Okay? So that's one characterization that we can start to see for graphs. And generally speaking, if the graph is undirected, do we need to bother drawing the arrowheads on the relationship? No. You certainly can. You can put arrows at both ends. It's not wrong, but it's just sort of redundant. If it's an undirected graph, the directionality doesn't matter, and just draw the line. And so, for example, we had sort of our 6-vertex graph from before. This was an undirected graph. Again, notice there were no arrows on those edges. So what that's implying is vertex 4 is related to vertex 6. Vertex 6 is also related back to vertex 4, whatever the relationship was. And then we could instead put arrowheads on those and make it a directed graph, where now vertex 1 is related to vertex 6. But is vertex 6 related back to vertex 1? No, it's not. Okay?
So can you have a graph for which some relationships go both ways and others do not?
Okay, so can you have a graph where some relationships go both ways but others don't? So first of all, when you're making a graph, you should only be using one relationship. If you've got multiple different types of relationships between the different sets of objects, then each relationship would make a graph. I mean, if you want to get technical, you can superimpose them by using like different colors or dashed lines or something. That's going to get really complicated to read. And so then in that sense, the relationship either is symmetric or it isn't. Now, it's certainly possible in an asymmetric relationship where we do have to worry about the direction. Could we just as easily have drawn an arrow from 4 back to 2? Yeah, we could. It's possible that you'll find a set of vertices where the relationship is symmetric in that case. But if it's not guaranteed to be symmetric for all cases, you would still call it directed and you would draw the arrows going both ways. Great question. Thank you. Does that make sense to everyone? Okay. So we've got directed and undirected. Second idea that we can consider, and this isn't going to be so critical for this unit, but it will be when we come back to the Google Maps unit later in the semester, is we can ask sort of and introduce the idea about weighted graphs. And so what we're now going to do is, again, consider what is the relationship between these vertices and between these objects that we're trying to describe. For the directed graph, we said, is it symmetric? For the weighted graph, what we're going to want to consider is, are all of the relationships the same? Okay? And so the way to sort of think about this is look at a couple examples. So in our Wikipedia example, what was each link? What was that relationship between those two pages? What did that represent? It was just a click. It was just some link from one page to another. Was there really any difference in the link between pages XKCD and Velociraptor versus the link between Velociraptor and Jurassic Park? Were those links really any different? No. Here's one click. Here's another click. For our journey to the center of the Earth, there's click, 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 click. But all the clicks were basically the same. Okay? So now contrast that. If we wanted to go back and think about a maps example, okay, so now we've got a whole bunch of landmarks or cities or intersections and all that, and the edges between those vertices, between those cities, are distances of the path, whether it's on the interstate, whether it's, I don't know, on the train, whatever the case may be. Are all of those edges the same? Is the distance, maybe we're looking at distance between them. Is the distance between New York City and Boston the same as New York City to Los Angeles? Not even close. So we can incorporate that amount of information to say that those links, those flights, we can fly from JFK to Boston Logan. We can fly from JFK to LAX. But those are not equivalent relationships because that distance or that time or that cost is going to be different. Okay? And so that's now getting at the idea of the weighted graphs or not. And so if all of the links, all of those edges are the same fundamentally, then the graph is not weighted. Because all we need to know is, are the different vertices connected? And that tells us everything we need to know. Versus if the relationship isn't equivalent, again, there's different flight times or different costs, maybe we want that information associated with the edges because that's going to help us solve a problem. Again, that's not going to be so critical for this unit, but just sort of preview of coming attractions. And so this is what we get now. If the edges are inequivalent, we can per se associate a number with them. We'll call that number the weight. And then when we draw the graph, what you'll see is that each of these edges now has this number. So like between New York City and Boston, it's 191 in this case. That's roughly the miles, I think, on I-90 driving between the two. If you want to take I-80 from New York City to Chicago, it's about, it's 95 between New York City and Boston. I-80 from New York City to Chicago, it's about 722 miles. Okay? And so we can put these numbers on those edges to tell us what is sort of that weight. And this forms now a weighted graph because we've got these different weights associated with the different edges and the different relations. Okay? So we've got directed and undirected, weighted and unweighted. And the last distinction that we're going to make, which is very relevant for what we're about to talk about with the kidney donations, is this idea of a cycle. So the idea now is in the graph is we're looking at sort of different paths through the graph, whether it's undirected and we can go either way between two vertices, or if it's directed where it's one way. Can we find a closed path within the graph? Which is to say, if I start at vertex 1 and I start moving through the graph, do I at some point, or can I at some point, return to vertex 1? Okay? Any such path that starts and ends at the same vertex is called a cycle. If a graph has a cycle, just one cycle, the graph is called cyclic. And if the graph has no cycles whatsoever, then the graph is called acyclic. Okay, so we can see an example. So here's a graph. So first of all, let's start to use our different terminology. Is this graph directed or undirected? It's undirected. And how do we know it's undirected? There are no arrows. Is it weighted or unweighted? It's unweighted. And how do we know that? Yeah, the edges are just sort of hanging out by themselves. There are no numbers or no weights associated with them. And so then last, is this graph cyclic or acyclic? Cyclic. Okay. How many cycles do you see in the graph? And I'll say just as a note, in an undirected graph like this, technically every pair of vertices forms a cycle because we could go from vertex 1 to vertex 6 and back to vertex 1. We're not usually interested in cycles of length 2 in an undirected graph because that just means they're connected. Okay? In a directed graph, cycles of length 2 are something more special. Okay? But for now, we won't consider those in this undirected case. But how many cycles do you see? I heard someone say 2. Does anybody agree with 2? Okay, a few hands. Does anybody have a different opinion? You see 4. Okay, anybody else want to weigh in? Okay, you see 7. Okay. So again, ignoring the 2 cycles, so we're going to say, well, 1 to 6 and back to 1 doesn't count. I see 3. And so they're shown here in different colors, which maybe aren't great on the projector, but they'll work fine on your computer at home. But we could start maybe at vertex 2, and we can see, well, we go from vertex 2 to vertex 4, 6, 5, and back to 2. And so that's a cycle of length 4, because there were 4 vertices in that cycle. We could also start at 2 and go to 3 up to 5 and back down to 2, giving us a cycle of length 3. And then lastly, we could sort of put those cycles together and go from 2 to 4 to 6 to 5 to 3 to 2, giving us a cycle of length 5. Okay? So there are those 3 cycles. All right? So now let's look at a slightly related graph. So we notice we've still got the same sort of 6 vertices, but now is this graph weighted or unweighted? Okay, it's unweighted because there's still no numbers with those edges. Is this graph directed or undirected? It's directed because we notice there are sort of all of those arrows on the edges. And is this graph cyclic or acyclic? Okay, so it's cyclic. How many cycles are there? Okay, I heard someone say 1. Does anybody have a different opinion? You think there are 3? Okay, so what 3 cycles would there be? Okay, so we said maybe the same 3 as before, but the issue now is, so 1 is the correct answer. We can look. So we can see there's still this cycle of length 3, so we can go from 2 to 5 to 3 and back to 2. But the other ones are broken because notice, if we started at 4, are there any edges that actually bring us back to 4? No. So can 4 be part of a cycle in that case? No, because if you start there, you can't ever get back. And so we could go from 4 to 6 to 5 and get into this 3 cycle. We could go from 4 to 2 and into that 3 cycle. But there's no way to get back to 4. So even though it sort of looks appealing to the eye to say, well, we've still got that quadrilateral, we've still got that cycle, because of the direction of those edges, that's not actually a cycle. We can't start at 4 and sort of move along and get back. Okay? Does that make sense? Yeah. So in this one, so they're in the different colors here, but you can see, so there's this one sort of in the blue dashed line going between sort of the triangle between 2, 3, and 5. There's the quadrilateral from 2 to 4 to 6, 5, and back down to 2. And then you can actually go around all 5 of them on the outside. Yep.
For weighted graphs, what does the number represent?
So what does the number represent? That's going to depend on what your relationship is. So the idea, again, we've got these edges which say 2 vertices are related. The weight is going to depend what is that relationship. So what we'll see when we get to the Google Maps unit in a couple weeks is maybe we're interested in what's the distance between 2 points. We might be interested, if you're thinking about like Google Maps actually giving you driving directions, what's the time it takes to get between the 2 points. And so those are all different numbers that we could put with it. They're going to be correlated in that sense, but they may not be exactly in the right order, because of speed limits or traffic or things like that. The shortest route in distance is not actually the shortest route in time. But so that's going to depend on what specific relationship you're looking at for.
When we're doing a path, should we always go to the one with the most edges connected to it?
When you're looking for a path, should you always go to the one with the most edges connected to it? Not necessarily. Again, that's going to depend on sort of what you're looking for. That's going to be application dependent. That's usually not maybe a bad place to start because it's so well connected. But it may not always be in the ideal solution. Okay? So any questions on graphs or characterizing graphs before we sort of jump back and start to bring this back to our kidney donation examples? Okay. So I guess maybe one more comment before we do that. Just for different types of problems that are typically encountered in graph theory, usually a lot of times these algorithms are related to how do we traverse or explore a graph. So this is like what Google Maps is doing when it's trying to make you recommendations. It has this big graph of all of these points, and it tries to explore it to say, how do I get from point A to point B? That's a very common problem. Okay? And so it turns out there's a whole bunch of questions that can be asked. Maybe what's the shortest or longest path? Are just 2 vertices connected? Can I get from vertex 1 to vertex 2 going along the graph? Okay, so if we go back to our directed graph example here, can we get from vertex 6 to vertex 1? Is there a path between those 2? Between vertex 6 to vertex 1 on the right graph here? No, we can't get from 6 back to 1. We can get from 1 to 6, but not the reverse course. It's sort of like a one-way street. Okay? So these are types of questions, and then actually, certainly a question that a graph theory will spend a bit of time asking is just, is the graph cyclic or acyclic? That's not, again, as these graphs get bigger and bigger and bigger and bigger and bigger, it's not always obvious how that's going to be. But we're not going to see necessarily examples that big working here. So by now, you've probably figured out, since we've spent the better part of the last hour and a half talking about graphs, that they're going to be relevant for helping us work with organ donation in these kidney exchanges. So now the question is, how? Okay, so if we start to think about now applying these graphs and these tools to looking at organ donation, what are our vertices going to be? Okay, so we know they're going to help somehow, but what would we actually have our vertices be? What would the edges be? So what are the things that we're talking about? What are the vertices? What's the relationship between them that we might want to look at when we're thinking about organ donation? Does anybody have any ideas? Yep. Okay, so the vertices would be two people, and specifically they would be the, right, so the donor and their acceptor that are paired together. Okay, so that could certainly be the vertex. Okay, so we have all of these different pairs of people. What are the relationships between them going to be? It could be blood type, but maybe we can generalize a little bit more. Well, so the body part, well, let's assume we're talking just about kidneys because we want to do this whole live donor thing. Yep. Can they donate to? So we now have, here's vertex 1 that has a donor and acceptor. Here's vertex 2 that's a different donor and a different acceptor. Can vertex 1 donate the kidney to vertex 2? Okay, that's one possible relationship we might want to consider. Is that going to be relevant to helping us determine how do we distribute these kidneys around? Sure. And so some of the other questions we might then want to address as we're thinking about setting up this graph, is this graph going to be directed or undirected? If we go under this premise where we're going to have the vertices are a particular donor-acceptor pair, and the relationship is this donor can give to that acceptor, is that a directed or undirected relationship? It's directed, because if vertex 1, if donor 1 can give the kidney to acceptor 2, does that mean donor 2 can give to acceptor 1? Not necessarily. That may be true, but it may not be. So this would certainly be a directed, it's an asymmetric relationship which would lead to a directed graph. Is this relationship weighted? Anybody? Yes or no? Maybe? Unclear? Okay, yes. So what would the weights be? Yep.
I mean, if we're considering live people, then it would be weighted, but the weights would be kidneys.
Okay, so maybe the weights are just one kidney, because maybe we could say the weight is, well, how many kidneys are we transplanting? And in this case, they're all probably one. So would we necessarily bother putting all the weights there? Because that sounds like they're sort of all equivalent. Okay, so it sounded like this might be sort of an unweighted relationship. We'll come back to that point. And do you think the graph is going to be cyclic or acyclic? It's probably going to be cyclic. Okay, because we're going to see some cycle. Because at some point, how many different blood types are there? Nominally 4. There's A, O, B, and AB. I'm glad no one said C. Okay. And so there's 4 blood types. If we've got 10,000 people in there, what are the odds that at some point you're going to be able to form at least some cycle between them? Unless there's just only that one person who has an AB type kidney, which is not statistically likely. Okay, so the idea though is as we're moving through this and looking at this discussion, these are the questions to keep in mind when we're designing the graph. We've come up with one possible way to do it. Again, to say vertex is a donor acceptor, and the edges, can they donate a kidney to a different donor and acceptor pair? That is not a unique way to do this. There might be other things. If we had other considerations in setting up our kidney exchanges, we might want to include those, and that might change how we sort of set up what are the vertices and what are the edges. Okay? What might an extra consideration that we want to take into account be? So far we've said we have a donor and acceptor, that's a vertex, and can they donate? What's another consideration we might want to take into account? Okay, likelihood of survival rates. Maybe just knowing blood type isn't good enough, but we want to have likelihood of survival rate. Okay, so that sounds like we've got a probability associated with each matching. So there's a 90% chance that donor 1 can give to acceptor 2, and there's a 10% chance that donor 3 can give to acceptor 2. This is now starting to sound like what kind of a relationship? It sounds like a weighted relationship. Because we can say, well, there's different numbers. These are not equivalent transplant operations. And maybe we can use that information in some way to better inform how do we set up our kidney exchanges. Okay, that's one way. What's another factor that we might want to take into account?
If you're getting the kidney from a random donor, not someone you know, then you have to account for distance and transport organs.
Exactly. So there's a logistical issue. Are the two people, so we can say biologically donor 1 can give to acceptor 2, but are they both in the same hospital? If they're not, do extra considerations have to be made? Yep. Okay, now if one's at Stony Brook Hospital and one's at another hospital here on Long Island, is that probably that big of a deal? No, because you're going to put the kidney on ice. You're going to spend an hour and a half driving it 3 miles. That was a rip on Long Island traffic. You're going to do it, but they're going to get the kidney there. But if you're in New York needing the kidney, and the person that's best matched with you based on all the biology is in Sydney, Australia, is that a match that we're as likely to make? Probably not, because logistically that's a lot more complicated to get the kidney there. So yeah, that's a consideration we might want to take into account when figuring out what are our vertices and what are our edges. There are lots of other things that we can do, and so we can always sort of make this more and more complicated, but we'll start with some simple examples for now. So as we put it, just to summarize, what we're going to do for the examples we're going to work here in class is say that each vertex is the donor-acceptor pair. So we've got one person who needs a kidney and one person who's willing to donate a kidney. And then what we're going to do is we start drawing the edges from vertex to vertex. What's the relationship? Is we're going to say a vertex an edge from vertex A to B means that pair B can accept the kidney from donor A. Okay, so the arrow sort of shows the direction that the kidney is going from donor to acceptor. Okay? And so as we've already sort of discussed, this graph is going to be directed. As we've already sort of mentioned, the fact that pair B can accept pair A's donated kidney doesn't mean you can go the other way around. Because that now depends on the blood type and the immunology and all of that of a different donor and a different acceptor. Okay? So it's a directed graph. The graph is going to be necessarily, for this simple example, unweighted. There's no difference between any one transplant versus the other. We're not considering logistical aspects. We're not looking at probability of survival. But these are certainly great things that we could build into this if we so wanted to. And is it cyclic? Well, let's look at some examples. So recall we had the 3 examples in lecture last time. And just to put them in table form, even though only the third one was, our first example is pretty simple. We had one donor pair, or donor-acceptor pair. They both had, I don't know, let's say A blood type. And so what would this look like as a graph? Okay, well, how many donors and donor-acceptor pairs do we have? We've got 1, so how many vertices will we have? We just have the 1. And how many different ways can we get the kidney from a donor to an acceptor? There's one way. We can take donor 1's kidney and give it to acceptor 1. So we get a really simple graph. So there's our vertex. We can label it 1. Meaning this is the vertex representing pair 1. And certainly the donor in pair 1 can give to the acceptor, so there's just a directed edge pointing back to itself. In practice, are we going to see things like this in these graphs? No, and why not? Would this ever get put on a registry? No, because if this happens, what are they going to do? They're going to get you both an operating room, and they're going to go do the transplantation. Okay. So this is it's a nice warm-up example, but it's not something you're going to see in real life. So now let's look at sort of the second example we had from last time. So how many donor-acceptor pairs do we now have? 2. So how many vertices are we going to have? 2. And what are the different ways that we can go about matching these kidneys? Well, can donor 1 give to acceptor 1? Nope. Can donor 1 give to acceptor 2? Yeah. Absolutely. And so, likewise, donor 2 can give to acceptor 1. And so we have our 2 vertices, and we see, now going back to your question, now there's the arrows actually running in both directions. In this case, it happens to be symmetric between vertex 1 and vertex 2, but that's not guaranteed to happen. And so first of all, is that graph now cyclic? Yeah, because if you start at vertex 1, we can take the 2 hops and get back to vertex 1. And so for the last example that we started with again today, here's our table. How many vertices are we going to have? We're going to have 4. And how many different edges are there going to be? We're going to see 4. That's what we discussed earlier. So we can draw it out. And just as we talked about at the beginning of class, if we start with pair 1, well, pair 1 can donate A. Well, only pair 3 can accept A. And so we have the one link going from 1 to 3. We could likewise go from 3 to 2, 2 to 4, and 4 to 1. OK, so we get this. Is this graph cyclic? Yeah. OK, so we can start to put this all together and sort of ask, what is it that we're actually looking for when we're doing these kidney exchanges? Do we want to see cycles? Yeah. Why do we want to see cycles? So that everyone gets a kidney, because we're assuming the donors are not magnanimous people. They're only donating so that their friend can get a kidney. And if their friend doesn't get a kidney, they're not going to give a kidney. Okay? So we need those cycles to make sure that everyone who's donating, their friend gets the kidney. So we have to come full circle back around. But then what are we actually looking for? So we're looking for cycles. What types of cycles in the graph? Okay? Maybe this is a good place to end for the day. I'll put this slide up. Think about this question over the weekend. And we'll finish up this discussion on Monday. So have a wonderful weekend. Thank you for your attention. And I will see you in 5 days.